Students, this is the next video for you. And last time we left off talking about chapter 5. And a few things that I wanted to reiterate or repeat because they're quite important are that sedimentary rocks are the only rocks that have fossils. Fossils are evidence of past life. And sedimentary rocks are layered, and that's why we call them beds. We can use principles of relative dating to figure out which sedimentary rocks are older and which ones are younger. And um, the study of sedimentary beds is called stratigraphy. And stratigraphy, I'll spell it for you, the study of sedimentary layering or sedimentary beds is a very important subscience of geology, and the person who does it is called a stratigrapher. We do it for many reasons. It's important to note that what geology is about, it's not looking at rocks. That no one cares about that. It's about making money, or it's about or it's about studying Earth history. Stratigraphers look for oil, natural gas, coal, gemstones, precious metals. Every single manufactured product, almost every manufactured product uses minerals. And therefore, if we're going to be successful in manufacturing products, we must have access to affordable mineral resources. Also, stratigraphers are involved in finding clean water and finding out ways to clean up our water supply. We need water for drinking. We need it for manufacturing products. We need it for farmers. And the supply of clean water is in danger of not being adequate or becoming too expensive. Stratigraphers are involved in that. Stratigraphers are involved in studying the history of our planet. That's what this class is about. So that's why we study sedimentary rocks. And some of you are doing really well in lab, and others are falling behind. And I worry about the ones who are falling behind. And I'm glad that some of you are getting them, are doing well in that. But you need to think about what you're looking at. Geologists are visual people. Here, if you're standing here at this roadside, for example, you can see layers of rock. And the first thing that should come in your mind is these must be sedimentary. And since they are sedimentary, then we know that the beds on the bottom are older than the beds on top due to the principle of superposition. We can also think next thing we would want to do if you wanted to study geology is you look at the rocks, these red rocks on the bottom, and figure out what types of rocks are they. Are they arkose? Are they siltstones? What are they? And what are these tan-colored rocks here? And then we'd find that once we figured out what types of rocks we're looking at, we want to look at the depositional environment where that rock formed. Where was the sediment deposited? Was this deposited on the land, perhaps? And maybe this on the ocean, in the ocean? And if that's the case, what does that tell us about this location in Utah? It tells us that perhaps a land environment deposited this arkose, and then sea level rose and covered up this area with a shallow ocean, depositing limestones. And then, if that's the case, maybe we can find fossils of marine organisms in these limestones. Principle of inclusions we haven't really talked about as much as some of the other things, but you need to know that here, if you got a granite here, granite is plutonic. It cooled underground. And so here's a sandstone bed here. And you've got chunks of the granite or inclusions of the granite in the sandstone. So you should automatically know without thinking, because on the test you don't have time to go through all your notes and everything. Wow, the sandstone has inclusions of the granite, so the sandstone must be younger than the granite. And then you want to figure out, how did that happen? Well, obviously this granite cooled underground, so the granite cut through some rocks which are no longer there. They've been eroded away. And then maybe this was a shallow marine area like a beach or a desert or whatever. Sand was deposited and chunks of the granite were incorporated into the sandstone bed. This situation over here is similar but different. Again, you have granite, which is a plutonic rock, and you have sandstone. But in this particular case, oh, actually, this is the same situation. I'm sorry. This is what happens after it's preserved. So here you can see some inclusions here of this darker colored rock. And which is older, the darker colored rock or this breccia? Which the older rock must be this darker colored rock, right? Okay. And relative dating. When you're looking at these, don't just think, oh, bed 1 was deposited, bed 2 was deposited. Think about the history of the area and geological processes, and it will make life a lot easier when you're doing relative dating. For example, here you got 2 different cross sections. In this particular cross section, first thing you want to do is look at the big picture, and then you can figure out the historical geology of the area. You've got bed 1, bed 2, bed 4, bed 5, and bed 6. They're all clearly sedimentary rocks. These are clearly sedimentary rocks. Here you've got a lava flow, so this is a volcanic rock. And you've got chunks of this lava inside of bed 4. So what happened here? You can do this. Bed 1 was deposited, then what? Then bed 2 was deposited, then the lava flow erupted onto the surface of the earth, then beds 4, 5, and 6 are deposited. However, this situation here looks to be quite similar to this one to the left, but it's different. Here you've got beds 1, 2, 4, 5, and 6, and 7, and you have a sill. A sill is plutonic. It's phaneretic. It cooled underground. And you've got chunks of layer 4 and bed 2 and bed 4 are in the sill. So this is a different situation, right? We know that since the sill has chunks of 4 and 2 in it, it must be younger than 4 and 2. So in this situation, what happened? Well, in this situation, first bed 1, 2, 4, 5, 6, and 7 are deposited, and then the sill intruded in between beds 2 and 4. Unconformities. We talked about unconformities before, and you got to know this, ladies and gentlemen. When you see that black wavy line, that's an unconformity. It means uplift and erosion. That means a mountain range rose out of the ground and was eroded away. That means there's missing geologic time here. In order to imagine how this works, let's take a look at 4 different columns of rocks. These are called stratigraphic columns. And the best way I could describe that for you is stratigraphers work with stratigraphic columns. So let's say we got into our vehicle and we drove and we went somewhere in Oliver Springs, and then we saw the following stack of rocks: shale, sandstone, limestone, sandstone, limestone, shale, sandstone, limestone, shale, limestone, shale, unconformity. So we can see the erosional surface. We see erosion here. Siltstone, sandstone, shale, sandstone, limestone. And we took out a ruler a tape measure, and we figured out how thick each of these units were, and we figured out which rocks they were, and then we could make this stratigraphic column. We'd make it on our laptop, or we could do it by hand. Remember, there's missing geologic time here. So whatever rocks were here are now eroded away, leaving behind this erosional surface. If you go to some other location, you find this stack of rocks. And you try to match them up. This shale belongs with this shale, this sandstone with this one, this limestone with this one. And then what? Well, then you got this sandstone is missing from here to here, right? And this rock is missing in these two columns. If it was so simple that you had the same stack of rocks everywhere, then you wouldn't be getting paid the big money to do stratigraphy, would you? Each of these represents a depositional environment. So let's say this was a lake. The lake did not extend between this location and this location. It pinched out somewhere between here. And so that's why this rock doesn't show up over here. So geology involves a lot of thinking. It's like a really complicated crossword puzzle, and you've got to figure it out. Okay. I hope that you can do. You're getting better at relative dating, and you need to have watched all of the previous videos, or it's going to be difficult. But if you are good at relative dating, you should be able to tell me the history of the Grand Canyon by looking at this picture. After you finish watching this video, go back to this picture and see if you can say it in your own words. If you can do that, you understand relative dating. A lot of people are intimidated by something like this. How in God's name am I going to tell the relative dating of the historical geology of the Grand Canyon, you might ask yourself? Well, it's not hard if you think of it like this. You've got all these different rocks here. All you got to do is find out as much as you can before you even get started. Break it down into little pieces, easily digestible, understandable pieces, and then you can move on and figure out the whole big picture. For example, I've got 1, 2, see these wavy lines? That's an unconformity here. There's another unconformity here. And there's another unconformity here. So how many unconformities do we have? En français, 1, 2, 3. We have 3 unconformities here. 3 uplifts and erosions. 3 mountain ranges that existed in the past that were eroded away. Missing time represented by these 3 unconformity surfaces. Notice that they mark what type of unconformity it is, but you need to be able to recognize it if these words weren't here. This is an angular unconformity here because you've got beds dipping to the right, which is dipping to the east. East is always to the right here. And above you have horizontal beds. So this is an angular unconformity. This unconformity here is a disconformity because you have sedimentary rocks above and below that are dipping in the same direction. This one's also a disconformity. Okay, that's the first thing you might notice. The other thing you might notice is all of these sedimentary beds going from the Tapiat sandstone, Bright Angel shale, Mauve limestone, the Red Wall limestone, the Supai group, the Hermit shale, the Coconino sandstone, the Toro Weep formation, and the Kaibab limestone. They're all horizontal, flat. But the sedimentary rocks underneath this angular unconformity are dipping to the east at about 40 degrees from horizontal. You also have a fourth unconformity here, is a nonconformity, where you've got whenever you see this pattern here, like this, that's metamorphic rocks. And this is igneous here. Zoroaster granite is igneous. So underneath this unconformity surface, you have igneous and metamorphic rocks. Therefore, this must be a nonconformity. So we actually have four unconformities: a nonconformity here, angular unconformity, disconformity, and disconformity. Next thing you might want to, you'll notice, okay, now that you know this is metamorphic rock, you notice that Zoroaster granite cuts through the metamorphic rock. Which is older, the metamorphic rock or the granite? The granite is what? The granite is younger because it cuts through the metamorphic rock, right? Okay, one more thing, and then you'll be ready to brag to your parents or to your brother or to your sister or your girlfriend or boyfriend or whoever, your friend. I know the history of the Grand Canyon. Let me show you how to do it. Okay, whenever you see limestones, almost always they were deposited in the shallow ocean. In a shallow ocean, anywhere from a water depth of 0 to maybe 100 feet deep, in the shallow part of the ocean. Okay, now let's talk a little bit about the history of the Grand Canyon. Also, here you can see your geologic time units. As you walk down into the Grand Canyon, or walking back into farther and farther back into history, we get to rocks that are 3.3 billion years old. That's what these metamorphic rocks are here. It's called the Vishnu schist. It's metamorphic, 3.3 billion years old. And the rocks up here are very young. They're only about 240 million years old. So these geologic time units tell you when these rocks were formed. All of these rocks here, underneath the unconformity, were formed in the Precambrian. That means before 542 million years ago. Then we get the Cambrian rocks, the first period of the Paleozoic is the Cambrian, then the Devonian, then the Pennsylvanian, then the Permian. And these are our youngest rocks. All of these rocks formed before the dinosaurs because these are Paleozoic rocks, and the Paleozoic era is before the Mesozoic era. So what happened to all of the rocks that should have formed during the time of the dinosaurs up to now? They've been eroded away as the Colorado River has cut through this area, removing a whole bunch of rocks. In other words, a new unconformity surface is being formed right here. Okay, so what's the history of the Grand Canyon? Well, 3.3 billion years ago, this metamorphic rock, the Vishnu schist, formed. Then, what happened next? The Zoroaster granite cut through the Vishnu schist. Then, uplift and erosion, forming a nonconformity. Then, this whole stack of rocks here, called the Unkar group, was deposited. Then the Unkar group was tilted by an earthquake. It was tilted. Then we had uplift and erosion, forming an angular unconformity. Angular unconformity. Not an angular disconformity. There's no such thing. It's an angular unconformity. Then the Tapiat sandstone was deposited. Then the Bright Angel shale was deposited. Then sea level rose and covered up this part of Colorado, depositing the Moave limestone. Uplift and erosion, forming a disconformity. Sea level rose again, covering this part of Colorado and depositing the Red Wall limestone. Uplift and erosion, forming a disconformity. Then the Supai group, Hermit Shale, Coconino Sandstone, and Toroweep Formation were deposited. Sea level rose, covering up this part of Colorado and depositing the Kaibab limestone. Sometime afterward, the Colorado River cut through and removed any rocks that are younger than 245 million years old. forming a new unconformity surface. Later on, sea level might rise again, covering up this whole part of Colorado and depositing limestone here on top of the Kaibab limestone. That's the historical geology of the Grand Canyon. So whenever you're thinking about sedimentary rocks, think about depositional environment. If you have a shale that formed in a lake, a lake doesn't continue forever, right? It ends somewhere. So let's say this is a lake deposit. You could find this lake deposit here. It might be thinner over here as the lake becomes more shallow, and then eventually you're going to get away and you're not going to be on that lake anymore. And then so if you move to another location, you're not going to find that lake deposit. So that's why we call sedimentary units facies, because they represent specific depositional environments. Okay, this is a short film, and I'm going to make another one soon, but we need to know what these two words mean, transgressions and regressions. Singular for that is a transgression and a regression. The plural is a transgressions and regressions. Transgression means that sea level rose and covered the land. At times in our past in North America, almost all of the 50 states were underneath the ocean. That means that transgressions have covered our continent in the past, depositing limestones. A regression means that sea level retreats, so the land is exposed. Whether or not you have a transgression or a regression depends on global climate. If the Earth is warming up, that means the glaciers are going to melt, and sea level will rise, and the oceans will invade the land, and you're going to get transgressions. The opposite of global warming is global cooling, when we have ice ages. When we have ice ages, what happens? Well, the ice grows on the North and South Pole, so there's less water in the oceans, and so the water retreats from the land. When the water retreats from the land, we have a regression. Usually when we have a limestone, that means, since limestones form in a shallow marine environment, that means we're looking at a transgression, doesn't it? Well, in order to understand by how do stratigraphers look at sedimentary rocks and stratigraphic columns and figure out, are they looking at a sequence of transgression where sea level was rising, or a sequence of regression when sea level retreats? In order to do that, we use something called Walter's Law. Why isn't it not Walter's Law? Walther's Law? Because it's German and the W is pronounced V, so it's Walther's Law, actually, Walther's Law. In the next film, we'll talk about Walther's Law and how stratigraphers look at stratigraphic columns like this one here and figure out, was sea level rising? And I know it was rising from here to here, for example. And then, so this is a transgression from going from 12 to 9. How did I know that? Well, that's in the next video.